Today we are going to be talking about chains. Not these chains, not these chains, and not these chains either. We're talking about polymers, specifically the polymer polyethylene terephthalate, which is a plastic. We will be looking at what it is, its issues in the environment, and how it can be enzymatically recycled. First of all, what is a polymer? In Greek, poly means many and mer means parts. Putting them together, you get many parts. And polymers are made out of monomers, aka one part put together, and they can have varying properties depending on how many monomers are in it, the structure of it, and how the chains interact with each other. Plastic is just one of the many polymers out there. As you already know, plastic is all around us, and it is very helpful. Why? Because it's cheap, strong, flexible, and long-lasting. Just like this 1 pound Rubik's Cube that I got from Primark that refuses to break. We can see why plastic acts like this by looking at polyethylene terephthalate, for example, or PET. PET's structure is repeating units of terephthalic acid and ethylene glycol. The terephthalic acid gives it a strong rigid section of its monomer consisting of rings and carbons double bonded to oxygens, giving it strength, while the ethylene glycol consists of single bonds, allowing it to be flexible at the same time. Hence why we see PET plastics everywhere, from your bottles to packaging to even your fabrics. Compared to other plastics, PET is 100% recyclable, and this might make you feel less guilty for using it, but it doesn't mean that there isn't a problem concerning its use. To begin with, not everything we use gets recycled, even though it can be recycled. In the US, the recycling rate of PET bottles and jars was around 30% in 2018. And in Europe, the rate was around 58% in 2017. And while that does sound good, it still means that the other 70% or 42% of PET plastic is just sitting out there, becoming things like microplastics that enter our food, getting ingested by other organisms, blocking their intestinal tracts, reducing their feeding stimuli, and causing death to many organisms. And that doesn't even account for the other PET plastics that aren't thrown in the recycling bins. Most of our garbage tends to end up in places like landfills or the sea. It's even gotten to the point where we've created a whole 1.6 million square kilometer patch of trash in the sea, nicknamed the Great Pacific Garbage Patch. And this is the size of France, times 3. Now, look at this picture. It's a picture of the garbage patch. See how many PET products you can spot. Well, most of the bottles that you can see in this picture are probably PET plastics. And so while PET plastics are 100% recyclable and some of it does get recycled, a lot of it ends up in places like this, accumulating in our environment. And because PET, like many other plastics, is hard to get rid of because of its strength, it persists in our environment. Current research can't say how long PET will take to degrade fully, but one thing most people say is that it'll take a long time. And this is why people are searching for sustainable ways to deal with PET. Chemical recycling is one option that is used currently. It breaks down PET into its raw components, ethylene glycol, and terephthalic acid, through the use of heat and chemical treatment. Mechanical recycling is also another option that people use, and this takes PET pellets and melts them together to form new products. The other option is enzymatic recycling, which utilizes organisms and their enzymes in breaking down polymers. Enzymes are proteins that help speed up chemical reactions in organisms, aka biological catalysts. They work by binding onto substrates, in this case PET, using the grooves within the surface of the enzyme called active sites. And by binding to the plastic, the enzyme can break down PET at really fast rates, compared to if it didn't have the enzyme. One enzyme, called leaf branch compost cutinase, or LCC, was isolated in 2012. And this enzyme was found to be able to break down PET at around 65 degrees Celsius. Enhancement of the enzyme allowed for the enzyme to work at 72 degrees Celsius, closer to the glass transition state of PET, as in the temperature that PET goes from a rigid solid to a soft but not yet melted material. This has possible uses in industrial recycling of PET. But what if we wanted to recycle PET in milder conditions, such as those in our everyday environment? In 2016, a team led by Dr. Koei Oda and Professor Kenji Miyamoto in Japan found a bacteria called Idenella saccharomyces that produced enzymes that could break down PET in 6 weeks at 30 degrees Celsius. Trying to isolate the enzyme responsible for breaking down PET, the team identified a section of DNA that translated into amino acids, sharing 51% of its sequence with another enzyme with the ability to break down PET. This other enzyme was found in the bacteria Thermobifida fusca. Upon isolating the enzyme, they found that it could hydrolyze PET into 2 main things, the major product being mono-2-hydroxyethyl terephthalic acid, or MHET, and the minor product being bis-2-hydroxyethyl terephthalic acid, which could then be hydrolyzed into MHET as well. Comparing Idenella saccharomyces to other bacteria that have been found to hydrolyze PET as well, it was able to outperform all of them at milder temperatures, earning its enzyme the name PETase. But it is not the only enzyme involved in hydrolyzing PET, because PETase can only break down PET into MHET and BHET. The MHET has to be broken down into PET's 2 main components, ethylene glycol and terephthalate acid. And this is where another enzyme, also produced by Idenella saccharomyces, comes into play. This enzyme is called MHETase. And it is able to break down MHET into terephthalic acid and ethylene glycol, bringing the life cycle of PET to a new beginning. In 2020, the effectiveness of PETase and MHETase was made even better by a group at the University of Portsmouth, led by Professor John McGeehan. They had discovered an engineered version where both enzymes were joined together, and this so-called super enzyme was 6 times as effective than before. It's similar to how Batman and Robin work. They work well on their own, but they'd be better together. The question we all might be asking right now is what makes PETase so effective at hydrolyzing PET? No one knows for sure what the binding mechanism of PETase is at this point, but the structure of the enzyme does tell us quite a bit about how it does its job. First of all, compared to the other enzymes, PETase has a wider active site. As seen by the side-by-side comparison between PETase and another enzyme that hydrolyzes PET, TF-cut, the active site of PETase is much larger. Therefore, it allows PETase to effectively bind to larger PET chains. Beyond that, PETase has 2 disulfide bridges, unlike the others, which only have 1. When the disulfide bridges are disrupted, the effectiveness of PETase is impaired, and this is because one specific disulfide bridge, DS1, links loops on the enzymes that contain the catalytic acid and the catalytic base. Additionally, the disulfide bridge allows for one of the loops to be extended, possibly making it a subsite that can bind to PET. So we now know that PETase can be a wonderful solution to the plastic problem we have in our world, well, at least for the PET side of the plastic problem. But the discovery of PETase was quite recent, and the engineering of the superenzyme based on it is even more recent, having been found in 2020. So what does this actually mean for our future? In the near future, the discovery of PETase probably doesn't mean too much. PETase and MHETase exist because the bacteria evolved in conditions where it needed to use PET as a source of energy. And because PET has only existed for not that long in the grand scheme of things, the bacteria and its enzymes aren't as effective as they could be, especially since the discovery of the enzyme was only made 6 years ago, compared to microbes that have had millions of years to evolve and decompose things like organic matter. Some plastics are also modified, and they have to go through even more processing before they can be broken down by enzymes like PETase, which, even though is fast at what it does right now, needs to be faster if it is to be used on a larger scale. These modified plastics could even have harmful chemical additives that would be fine stored in undegraded plastic, but when degraded by enzymes could have adverse effects in the world. And if we want to use these enzymes to break down PET in our everyday world, not in industrial plants, then this could be harmful. In the far future, enzymatic recycling could be huge in keeping our environment clean. But for now, because it is still all kind of new, we have our own responsibilities in keeping our environment clean by steering away from single-use plastics and switching to reusable alternatives. The best way to avoid pollution is to not pollute.